Okay, chapter 6 of chemistry, starting with physical and chemical changes. So physical changes do not alter the chemical makeup of the substance. Chemical changes do not alter the chemical makeup of the substance. So, for example, if you boil water, it is still water once you've boiled it, and it does not change the chemical. It is still H2O. Before you boil it, after you boil it, when you freeze it, it's still H2O. A physical change can be easily reversed. So, for instance, if you're boiling a pot of water, if you put a lid on the pot of water, the water will condense and go back into the liquid form. The gas, you can trap that gas and it'll go back into a liquid form. If you took an ice cube and you took some water and you froze it into an ice cube, you can get it back to the liquid form by melting it. So phase change is one example of a physical change. Another example of a physical change would be if you dissolved sugar or salt in a glass of water. You mix the salt in with the water. Could you separate it back out? Sure. Boil the water or pour it on a plate and let it evaporate, and just the salt will be left in there. So if you can reverse the change, it's a physical change. Chemical changes alter the chemical composition of the substance. They completely make a new substance. So an example of this would be wood burning with oxygen in the air to make a fire and becomes water, carbon dioxide, and ash. You take wood, you combine it with the oxygen, and you end up with water, carbon dioxide, and ash. It's completely new substances. You cannot easily reverse a chemical reaction. Some chemical reactions can go back, some you never can. If you burn wood, you cannot take the ash and the carbon dioxide and try to put back and make a log of wood. It doesn't go backwards. An example of a physical change is temperature changing. We kind of talked about phase change there. Temperature change is a physical change. We measure temperature change in either Fahrenheit, Celsius, or Kelvin. We are not currently going to talk about Kelvin, but it is one that they use sometimes in science. Typically, we're going to use Celsius in science. We're used to using Fahrenheit when, it's 70 degrees outside. We're talking Fahrenheit. Science often uses Celsius, though. Celsius is nice because the boiling point of water is 100 degrees. The freezing point of water is 0 degrees, and that's where the Celsius scale is made from. In Fahrenheit, you boil at 212 and you freeze at you freeze at 32 degrees and you boil at 212 degrees Fahrenheit. So it's kind of a funkier scale. Celsius is all done on 100 scale there. You obviously can go below 0 on Celsius, just like you can go below 0 on Fahrenheit. If it's 10 degrees below 0 outside, you're in Fahrenheit. You can go below 0 on Celsius too. Okay, converting between them. I give you both equations to go from Celsius to Fahrenheit and Fahrenheit to Celsius. You need to practice using the equations. You can put them on your little cheat note sheet. That's fine. You can have the cheat sheet for them. Example 6.1. Most chemists define room temperature as 25 degrees Celsius. What is that in Fahrenheit? So, let's bring the board up here. We have 25 degrees Fahrenheit, and we want to know what it is in Celsius. So we're going to use the second equation on our sheet, which is temperature Celsius equals 5/9. Hold on. We're in Celsius. We want to go to Fahrenheit. Wrong way. Use the other one. Temperature Fahrenheit equals 9/5 temperature Celsius plus 32. Remember what I told you in class. Start with the parentheses and then do things outside the parentheses. So temperature Fahrenheit, let me prop this up so it's a little higher. 9/5 times the temperature Celsius is 25 plus 32. Temperature Fahrenheit, so 9/5 times 25 is going to be 45 plus 32. So the temperature Fahrenheit is going to be 77 degrees. Okay? So all you gotta do is just plug the numbers in. I gave you both equations. If you're gonna do the other direction, let's see. Let's do the other direction. Let's go from Celsius to Fahrenheit just to make sure you can see how to use the equations. So, hold on, I get the lid off the marker again. That should not be so hard. It gives you the hottest temperature ever recorded is 134 degrees Fahrenheit. Whew. At Furnace Creek Ranch in Death Valley, California. What is that in degrees Celsius? So we have 134 degrees Fahrenheit. So we're trying to go to temperature Celsius. And we know that that's 5/9 times temperature Fahrenheit minus 32. Temperature Celsius equals 5/9. The temperature Fahrenheit is 134 minus 32. 5/9. We do the parentheses first. 134 minus 32 gives you 102. And then we multiply by 5/9. You can, if your calculator's a little trickier, if you have the scientific one, you might be able to enter that. If you can't, just find the decimal for 5/9. Just do 5 divided by 9. It'll give you a decimal. I don't know that off the top of my head. And I can't do it while I'm on my phone giving the video because that's where my calculator is. But that, when you do that, it's 56.7 degrees Celsius. If you divide this out, the 5/9 and get a decimal point, or the 9/5 for the other one and get the decimal point, feel free to write that on your little cheat note sheet. Okay, and then you can use that decimal point instead of 5/9, so that it's not, I don't want that to hold you up at all. Okay, so that's how we just transfer from Fahrenheit to Celsius or Celsius to Fahrenheit. Okay, phase changes. So moving from one phase to another, a solid to a liquid to a gas, or a gas to a liquid to a solid. There's also a plasma state. We're not going to talk about plasma in chemistry. Okay, so you can see I gave you a little diagram there that shows solid going to liquid. If you go from a solid to liquid, you're melting. If you go from a liquid to gas, you're vaporizing. If you go from a gas to a liquid, you're condensing. If you go from a liquid to a solid, you're freezing. If you go from a solid straight to a gas, it's sublimation. If you go from a gas straight to a solid, it's deposition. If you go from a solid, as you go from solid to liquid to gas, you are adding heat. So I want you to draw an arrow at the top of that picture. Let's see if I can make this so you can. So here you have solid. Then you have liquid. And you have gas. As you go from solid to liquid to gas, you are adding energy. You add energy to go from solid to liquid to gas. That makes sense, right? If we want to boil, we have to add energy. We put it on the stove and we turn on the heat. As you go from gas to liquid to solid, you are removing energy. Gas to liquid to solid, you are removing energy. Adding energy, removing energy. Stay. Okay. Kinetic theory of matter says that molecules that make up a substance have space in between them and are in constant random motion. So every substance, so this pen, has a bunch of molecules making it up. And these molecules are constantly moving in random motion. You can't see them, but those little tiny molecules are moving. The hotter the substance, the faster they move. So as we add energy, we're making molecules move faster. And as the molecules move faster, that makes it change phases. So the molecules that make up a substance have space in between them. Molecules aren't so tightly packed. There's space. If it's a solid, there's less space. A liquid, there's more space. And a gas, there's even more space. The hotter the substance, the faster they're going to move, the faster the motion. The different phases are really just different just the difference in distance between the molecules. As we add energy, the molecules move faster and then have more space in between them. If you're moving faster, you're going to need more space because things are going to have to move around. Okay, I gave you a picture there of, I don't think this picture's in your book. Yeah, there is one in your book on page 170. As you add heat, you can see that you stay in a solid and then you get to a certain temperature and you melt. Different substances will melt at different temperatures. It melts. It stays at the same temperature until the whole thing is melted. Then it's a liquid and it goes up in temperature and it stays a liquid. When it gets to the boiling point, it boils. Boiling point can vary based on which substance it is. Then it boils and it stays at the same temperature until it's all boiled. And then it's a gas. That's why your pans, if you're boiling a pan of water, as hot as it's going to get is 212 degrees Fahrenheit or 100 degrees Celsius. That is why pressure cookers exist. If you've ever canned, or now they even have the Instant Pot pressure cookers, the reason for that is because you can actually make it get hotter faster because you're adding pressure, and as you add pressure, you're condensing those molecules, which means they can't move as much, which means, so we're going to get into Boyle's laws. We're going to get into the gas laws. Boyle's law is one of them later, but that is the case. You can't, as you're boiling, you stay at that same temperature. It does not go up until you're done boiling, and then it's a gas and stays at that. Good, can go up. Now, water is an exception, and you know this, you've heard this before, because ice floats, right? That means that the solid of water, which is ice, the molecules are further apart than the liquid of water, which is water, liquid water, right? Why? It's the only substance that does this, where the solid is actually more spread out and therefore less dense. Most likely it's just the way God made it, because it allows lakes then freeze from top to bottom. So the top of the lake can be completely frozen. It can have inches of ice on it. But the wildlife, all the fish and things, can stay living at the bottom of the lake. Otherwise, if water was like every other substance, it would freeze from bottom up, and then all the fish would die in the lake, and then you wouldn't have fish in the lake ever. So this allows it, and actually it insulates it, makes it kind of warmer under there. So it allows it to stay liquid, and it freezes from top down, just the way God made it. Okay, chemical reactions. So a lot of chemistry is talking about taking different elements, different molecules, compounds, and somehow combining them to make new compounds, taking them and making reactions. So in a chemical reaction, atoms involved get rearranged to form new chemicals. So you can see in your picture, I show you the reactant side and the product side. The reactant's on the left, the product is on the right. We did balancing equations in class this week, so you saw that. We always have reactant side, those react and they make a product. We have coefficients. Remember we talked about we can change the coefficients that are in a chemical reaction. We can never change the subscripts because those are written based on what substance it is. If you change the subscripts, you're changing the substance. So you can't change the subscripts. Okay? We're going to stop there. If you want to get ahead, it stops you. Today's lesson stops at looking if equations are balanced, which you learned how to do in class. We also talked about how to balance them, which is what the next section's on. If you want to get ahead, you could start working on doing the balancing equations. You don't have to, but just so you know, that's where it's going from there. Okay.